viewers. In our today's session, we are going to discuss about ordinary differential equations. But we are going to solve this ordinary differential equation using the Laplace transform. What are the ordinary differential equations? We understand that an equation like this one, a dy with respect to dx, we add to b y is equals to k is being referred to as an ordinary differential equation. We can also have a dy squared with respect to dx squared. We come and add to b dy with respect to dx. We add to c y is equals to k is being referred to as an ordinary differential equation. Here we are having a first order differential equation. Here we are having a second order differential equation. In our session for today, mostly I'm going to dwell about the second order differential equation. Let us now get into our discussion on second order differential equation using the Laplace and transform. Then later we shall discuss about the first order differential equation using the Laplace transform, whereby on this one mostly we shall discuss about the simultaneous equation of first order differential equations. When you've been given a dy squared with respect to dx squared, we come and add to b dy with respect to dx, we add to c y is equals to k. The first and the most important thing that we need to understand when simplifying an equation like this one is that we must first get the Laplace transform of dy squared with respect to dx squared, the Laplace transform of dy with respect to dx, the Laplace transform of y, and the Laplace transform of k. What is the Laplace transform of dy squared with respect to dx? We understand that the Laplace transform of dy squared with respect to dx squared is equals to s squared y bar. We subtract from sy, we subtract from y naught, we subtract from y1. This is now the Laplace transform of our differential here. The Laplace transform of dy with respect to dx is equals to s y bar, we subtract from y naught. And lastly, the Laplace transform of y is equals to y bar. Here the Laplace transform of our constant we know is going to be k all over s. Once you understand all this, now you are good to go. Let us now simplify whatever we are having here, but this is the most fundamental concept that you need to understand when you are handling ordinary differential equation using Laplace transform. In our first step now, we are going to have we come and introduce the Laplace transform of dy squared with respect to dx squared. We come and add to b, we introduce the Laplace transform of dy with respect to dx. We add to c, we introduce the Laplace transform of y. And lastly, the Laplace transform of k. This is our first step. Now, we need to find the Laplace transform of dy squared with respect to dx, whereby we say that The Laplace transform of our function here is equals to s squared y bar we subtract from y naught we subtract from y1. Sorry, here I'm supposed to be having s because it is a second order linear equation. We come and add to b. The Laplace transform of dy with respect to dx is equals to, we are going to have s y bar we subtract from y naught, first order linear equation. We come and add to c. The Laplace transform of y we agreed is equals to y bar, and lastly the Laplace transform of k is equals to k all over s. From this up to this point now, what we need to understand is that the conditions of y and y1 are always given in the equation, whereby when you've been given literally to solve a kind of a differential equation using the Laplace transform, you will always find that y we can come and say is equals to v, and you will also find dy with respect to dx is equals to, let's say, z, because here we are doing our derivative. I'm just showing you on how you can go about the introduction part of ordinary differential equation using the Laplace transform. So when you have these terms this way, you need to understand that y will always be equals to y naught, and dy with respect to dx will always be equals to y1. That is all you need to understand, to mean that now we are going to have a into s square y bar we subtract from s, but we say that y naught is equals to y here, to mean that we are going to replace now with v. We come and subtract from y, dy with respect to dx is equals to y1, to mean that we are going to have z. We come and add to b into, here we are going to have s y bar we subtract from y naught which is equals to v. We come and add to c y bar, everything is equals to k all over s. We can come and open the bracket, and now we are going to have a s squared y bar we subtract from s v, sorry, we subtract from s a v we subtract from z a. We add to b s y bar we subtract from b v, we add to c y bar, everything is equals to k all over s. Now at this point we can come and collect the like terms of y bar, to mean that y bar into, we factor it out, a s square we come and add to b s has got a y bar of which I'll factor it out here. We come and add to c, y bar is outside here, and now we are going to have is, we subtract from s av, we subtract from z a, we subtract from b v, everything is equals to k all over s. From this point now we can come and have y bar into as square, we add to bs, we add to c, is now going to be equals to, we are going to have k all over s, all these unknowns that we are having this side, they are going to cross the equal sign to the other side, and we are going to have a positive of now a s v here. We add to za, we add to b v here, all over 1, all over 1, all over 1. We can simplify our equation on this side by saying that we take whatever we are having within the denominator, we multiply by everything. To mean that now we are going to have k, because when we take 1, when we take s, we multiply by this, we are going to have k. We come and add to as squared v. We add to s za. We add to s b v, and everything is going to be all over s. Here now we are going to have a y bar into a s square. We add to b as we add to c. We need to have y bar on our left hand side, to mean that we are going to divide by a s square. We add to b as we add to c. On this side now we are going to have a s squared. We add to b as we add to c. To mean that these two will cancel out, and now we are going to have y bar is equals to as squared v. We add to sz a. We add to sbv. We add to k. Everything all over s into a s squared. We add to b s. We add to c on our denominator. When we check here, we need to have our term of y on our left hand side. And how can we get y on our left hand side? We understand that the Laplace transform of y is equals to y bar. To mean that the inverse Laplace transform of y is the inverse Laplace transform of y bar is going to give us y, is going to take us back here. When you introduce the inverse Laplace transform of y here, for us to have our term of y, also on this side we are going to introduce our inverse Laplace transform. And when we introduce the inverse Laplace transform of y on our right hand side, now here we can come and have y is equals to everything on the other side. And now we can start using partial fraction in solving our inverse Laplace transform from this point. Let us now get into our first example. This is how you go about an ordinary differential equation like this one using Laplace transform. Let us now get into our first example.